Today we are going to answer a question that sounds almost magical. Why can an embedding vector represent meaning? Start with one word, cat. To a computer, cat begins as a separate symbol. The model cannot calculate with the feeling of the word. It calculates with numbers. So the first move is to turn a word into a list of numbers. That list is called a vector. You can think of the vector as a coordinate for a point. Cat has a point. Dog has a point. Car has a point. If those points were placed randomly, they would not mean anything. The important part is that training slowly moves those points around. Words that appear in similar contexts get pulled towards similar areas. For example, cat and dog often appear near words like pet, food, bark, and cute. So the model has a reason to place them close together. Car often appears near road, speed, engine, and traffic. So it tends to land farther away from animal words. That is the first intuition behind semantic space. Similar meaning becomes nearby position. Real embedding vectors may have hundreds, or even thousands, of dimensions. We cannot draw all of those dimensions on a screen. So we compress the idea into 2 or 3 dimensions on screen. One direction might roughly separate animals from vehicles. Another direction might roughly separate concrete objects from abstract ideas. One more direction can express one more kind of difference. But a single dimension usually does not literally mean cute or fast. Meaning is encoded by many directions working together across the whole space. This is why directions are just as important as positions. The direction from king to queen may capture a shift in gender and role. The direction from man to woman may capture a related shift. So a vector does not only say where a word is. It can also say how one meaning changes into another meaning. Now we need a way to compare two vectors. A common tool is the dot product, often used as cosine similarity. If two vectors point in almost the same direction, the angle between them is small. Cat and dog point in related directions, so their score is high. Cat and engine point in very different directions, so the score is low. But the geometry comes from a huge amount of text. During training, the model sees which words can replace each other, appear together, or play similar roles. The training objective rewards better prediction. To predict better, the model has to pack useful language relationships into numbers. So an embedding is not a handwritten dictionary. It is a map the model builds while trying to predict language. Of course, this map is not perfect. One word can have multiple meanings. Apple can mean a fruit. Apple can also mean a company. A single word embedding may give only an average impression. Inside modern language models, later layers keep updating that representation with context. Apple tastes good and Apple released a chip should not end up in the same place. The context changes the final meaning. That is why embeddings are the entrance to language understanding, not the whole story. This also explains why retrieval augmented generation, or RAG, uses embeddings so much. First, split documents into chunks. Then turn every chunk, and the user question, into vectors. Then search for chunks whose vectors are closest to the question. If you ask why video memory matters, the system does not start with exact word matching alone. It places the question into vector space and looks for nearby chunks. Chunks about GPUs, model parameters, bandwidth, and training cost should rise to the top. That is why a vector database can feel like a search engine that searches for nearby meaning. Vector search can still make mistakes. Two phrases may look related because they appear in similar articles. A new meme, product name, or rare technical term may have an unstable position. So reliable systems usually do not trust one vector score alone. They add keyword filters, a re-ranker, context windows, and sometimes human rules. The embedding gives a strong first guess. The later steps judge the details. Once words become vectors, the model can do 3 useful things. First, it can measure distance and ask which meanings are close. Second, it can use direction to represent a relationship or attribute change. Third, it can use dot products to turn similarity into a trainable number. So the short answer is this. Embeddings represent meaning because training compresses co-occurrence, substitution, relationships, and attributes into vector space. The numbers do not understand language by themselves. The structure learned from language makes the numbers useful. When you see a word become a row of numbers, do not think of it as only an ID. Think of it as the word's coordinate on a semantic map. The distances and directions on that map are the foundation for retrieval, reasoning, and generation.